In the previous videos, we looked at discrete distributions. Now in this lesson, we are going to focus on continuous distributions, where the random variable is continuous. So the first distribution that we are going to learn in this video is uniform distribution, and the notation is x follows uniform a comma b, where a and b are the parameters and x takes values between a and b. Now let's understand this from the area, because we can understand the probability in terms of area. So say this is the rectangle whose starting point is a and the end point is b, and suppose the area of this rectangle is 1. So the probability is also 1. So the total probability of 1 is spread evenly between limits a and b, so that the subintervals of the same length have the same probability. Now say this is breadth and this is length. On the x-axis we have random variable x, and on y-axis we have y. So suppose the length of this is fx, so we can say area equals to length times breadth. Area is 1, length is fx, and breadth is b minus a. So fx is 1 over b minus a, where x ranges from a to b, right? Now if you remember the definition of PDF, then the values of the function should be positive, and the integration in continuous, this integration of the PDF should be equal to 1, right? So here you can see the area is 1, right? The total probability is 1, and the values, because this area is on the first quadrant and a and b are the positive values and b is greater, right? So b minus a is certainly positive. Okay, so this satisfies the condition of PDF. So this fx is the PDF of uniform distribution. All right, now let's do one example. Let's say x follows uniform 2 comma 7. So the PDF is 1 over 7 minus 2, which is 1 over 5, and the range of x is greater than 2, less than 7. Okay, now let's look at the mean and variance. So the expectation of x is integration of x times PDF dx. So this is the range of x. Now here the range of x is a to b, x times, and PDF is 1 over b minus a dx. We can take 1 over b minus outside of the integration, and then the integration of x dx. The integration of x is simply x square over 2, and the range is a to b. So this is b square minus a square divided by 2 times b minus a. We can cancel out b minus a, so the expectation is the midpoint of the range, right? So this is b plus a divided by 2. Now let's see how we can derive the variance. For variance we need expectation of x square. So expectation of x square is integration, we replace x with the x square, and then the PDF, which is b minus a dx. The range of x is a to b. We can take this outside, and the integration of x square dx. So 1 minus ba, integration of x square is x cube divided by 3 in the range a to b. So this is b cube minus a cube divided by b minus a times 3. So we can expand this term, b minus a times b squared plus ab plus a squared divided by 3 times b minus a. We can cancel this out. So the remaining terms are okay. So this is expectation of x squared. Now the variance of x is expectation of x squared minus expectation of x. So this is b squared plus ab plus a squared. Okay, so this is a squared divided by 3 minus this is b plus a divided by 2 whole square. Now if we simplify this, we'll get 4a square plus 4b square plus 4ab minus 3a square minus 3b square minus 6ab, and the LCM is 12. Okay, so this is a square plus b square minus 2ab whole divided by 12, which is b minus a whole square divided by 12. So the variance of x is b minus a whole square divided by 12. All right. Now let's look at one example. Let's say the x follows uniform 0, 10. The PDF is 1 over 10 minus 0, which is 1 over 10, and the range of x is 0 to 10. Now if you are asked to calculate the probability x is less than 5, how do you do? So this is the CDF, right? If you remember the notation of the CDF, this is x is less than or equal to x. So this is the notation of CDF. So if we are able to find out the CDF of this PDF, then we can calculate this probability. All right. So let's see how we can derive the CDF. So the idea behind the CDF is simple, that is integrating from the lower limit up to some point x and then the PDF. Okay, so this is CDF. So in this example, the lower limit is 0, so we'll integrate from 0, and the upper limit is 5, so 5, and the PDF is 1 over 10 dx. So this is 1 over 10 times 5, which is half. Okay, so in general we can write probability x is less than or equal to x. We are integrating from a, x follows uniform a comma b, so the lower limit is a and the upper limit is x. We are integrating up to some point x and the PDF. Okay, so let's write fs, because we already have x on the limit, so we should use some dummy variable ds. Now a x, the PDF is 1 over b minus a ds. So this is x minus a divided by b minus a. All right, so this is the CDF, probability x is less than or equal to x. So whenever you are asked to calculate some probability, you can simply put the value of x in this formula and then you will get the probability. All right, so this is about the uniform distribution. Now let's move on to the next distribution, that is gamma distribution. So the notation is x follows gamma alpha lambda, where alpha and lambda are the parameters and alpha lambda are greater than 0, that is positive. Now before we derive the PDF, Let's look at the gamma integration first. In the previous video, we have already learned about the gamma integration, which is 0 to infinity, and the function is x to the power alpha minus 1 a to the power lambda x dx, and this is gamma alpha divided by lambda to the power alpha. Okay, now here let's bring this term to the left side. So this is infinity x to the power alpha minus 1 a to the power lambda x. So this becomes lambda to the power alpha and gamma alpha, and this is 1, right? Okay, we write it dx 1. So now you can see this integration of this whole term is 1, and the value of this term is positive. How? We are given that the alpha and lambda are positive, so you can see, and the range of x is positive. Okay, so certainly this term inside is positive. Okay, so this satisfies the condition of PDF. So we can say the PDF of gamma integration is x to the power alpha minus 1 a to the power lambda x lambda to the power alpha gamma alpha. All right, and alpha lambda are greater than 0. Okay, so this is how we can derive the PDF of gamma integration, sorry, gamma distribution. Now let's look at one example. Suppose x follows gamma 3 comma 5. So the PDF is 5 to the power 3 gamma 3 x square a to the power minus 5x, where x is greater than 0. All right, now let's see how we can derive mean and variance. So mean, so the expectation of x is integration x times PDF, and the range of x is 0 to infinity dx. So this is 0 to infinity x times PDF lambda to the power alpha gamma alpha x to the power alpha minus 1 e to the power lambda x dx. Now we can bring this term outside of the integration. So 0 to infinity, this is lambda to the power alpha gamma alpha x to the power alpha plus 1 minus 1, right? Here is 1, then e to the power minus lambda x dx. Now we can use the gamma integration because this is in the form of gamma integration and the limit is also 0 to infinity. So this is lambda to the power alpha gamma alpha. The formula of the gamma integration is gamma alpha divided by lambda to the power alpha. So here in place of alpha we have alpha plus 1, and in place of lambda we have just lambda. So this is gamma alpha plus 1 divided by lambda to the power alpha plus 1. So if we simplify this, we'll get alpha factorial divided by alpha minus 1 factorial times lambda, and this is simply alpha by lambda, right? So expectation is alpha by lambda. Now what about the variance? For variance we need to calculate x square. So 0 to infinity, in place of x we write x square and PDF. So this is 0 to infinity x square times lambda to the power alpha gamma alpha x to the power alpha minus 1 e to the power lambda x dx. Now again we can bring this term outside of the sum integration. Lambda to the power alpha gamma alpha 0 to infinity x to the power, now this time we have 2 in the power, so 2 plus alpha minus 1 e to the power lambda x dx. Now in place of alpha we have 2 plus alpha, and in place of lambda we have just lambda. So using the gamma integration we can say gamma alpha plus 2 divided by lambda to the power alpha plus 2. So if you simplify this, you'll get alpha plus 1 factorial divided by lambda square alpha minus 1 factorial. If we simplify this further, then we can say alpha plus 1 alpha and alpha minus 1 factorial divided by lambda square alpha minus 1 factorial. This gets cancelled, so we are remained with alpha plus 1 divided by lambda square, and this is expectation of x square. Now variance of x is expectation of x square minus expectation of x whole square. This is alpha times alpha plus 1 divided by lambda square minus alpha by lambda whole square. So this is alpha square plus alpha minus alpha square divided by lambda square, which is alpha by lambda square. So the variance of x is alpha by lambda square. Okay. Now after this, let's see how we can derive the CDF. In gamma integration, we'll never use the CDF of gamma integration to calculate the probability. Alright, we'll convert it into chi-square distribution, and then we'll use tables of chi-square distribution to calculate the probabilities. So when x follows gamma a comma b, then 2 lambda x follows chi-square 2 alpha. So this is the chi-square distribution, where this thing is the degree of freedom. Okay. So whenever x follows gamma distribution, we can say 2 lambda x follows chi-square 2 alpha. Okay. So for example, x follows gamma 2 comma 3, so this is alpha and this is lambda. So 2 times 3 times x follows chi-square 2 times 2, which is 6x follows chi-square 4, right? And this is the degree of freedom. Okay. So now how do we calculate the probabilities? Let's say you are given probability x is greater than 4. So we can write probability 6x greater than 24, right? I have multiplied by 6 on both sides. So this is probability chi-square 4. Okay, I replaced 6x with chi-square 4 greater than 24. And then I can write this 1 minus probability chi-square 4 less than or equal to 24. Now we are going to use the table, and in table you're only given the value for less than or equal to. You do not have the values for greater than. Okay, that's why I have changed greater than to less than or equal to. Now let's see how table looks like. So this is the table of chi-square distribution. As you can see, on the x-axis you have the degree of freedom. This is the degree of freedom, and on the y-axis you have the values of x. Okay, so the distribution probability is x less than or equal to x. All right, so we'll look for the value of this small x on the y-axis and the chi-square, the degree of freedom, on the x-axis. Okay, so in our case the degree of freedom is 4 and the value of x is 24. So you can see the degree of freedom is 4. So we'll look in this column. So let's see where is 24. So here we have 24. So this is 0.9999. Okay, so now we can say this is 1 minus 0.9999, okay, which is 0.0001. So this is how we calculate the probability of gamma distribution using the chi-square. All right, we'll never use the integration to calculate these probabilities or CDF. All right, so this is all about the uniform and the gamma distributions, and let's stop here, and I'll see you in the next video. Thank you so much for watching this video.